Okay, welcome everyone. Thanks for coming. Today I'm gonna walk you guys through some of the basics of using the OpenMind computing cluster, and hopefully you'll get a little bit more general information beyond that. I'd just like to start by thanking Emily, who's put this tutorial series together. This is the second round. Probably a lot of the people in this room came to a few of the awesome tutorials that happened last year, and we'll have a few more in the coming weeks. And also, I should thank the BCS seminar committee for supporting this series, as well as Kris from CBMM, who is going to be recording the lecture today. So anybody here can go back and review, or for those of you who weren't able to make it, you can watch offline. And now, just a little bit about where I'm coming from with this. I'm not a person who is very proficient in software developing. When I came here as a postdoc a couple years ago, I had never used a Unix terminal or written a shell script. But I found out that there was this great resource in the OpenMind computing cluster, and so I set out to learn how to use it. And at the time, I was like, "Wow, it would be really great if there was an accessible resource for those of us who have very little knowledge about all this stuff to get them going." And so, when Emily started her tutorial series, I thought that eventually, I had to do something like this. So here it goes. I hope it's not too much of the blind leading the blind, but I've learned quite a bit, the painful way about doing this stuff. So hopefully I can help some of you guys out as well. The objectives today are, first and foremost, to learn the basics of how to use OpenMind, which is a computing cluster managed using Slurm, which is the simple Linux utility for resource management. We're going to walk you through some example workflows, and hopefully you'll learn some best practices for effective usage of the cluster. More generally, you'll get to see some strategies for using remote computing resources. Along the way, you'll learn to use the terminal, which is just a command line interface as opposed to a graphical user interface, which most people are used to using these days. You'll get an introduction to shell scripting, and you'll learn some of the basics of Linux operating systems. So what is OpenMind? OpenMind is a set of managed computers, which we call nodes, accessible through a single portal, openmind.mit.edu, which enables users to perform computations which are infeasible or just maybe inconvenient to perform on their personal workstation or laptop. There are different types of nodes for different types of tasks. Most of the nodes have 20 cores, although it's up to 24. That should be, I thought it's 32. 32. I think one node has 32. Not a big difference. Most have 256 gigabytes of RAM, which if you start using the computing cluster for certain problems, can make a huge difference between how fast something runs on your computer versus an OpenMind node. And some even go up to 512 or 1 terabyte of RAM. There can be from anywhere from 0 to several GPUs. There's lots of disk space, 483 terabytes total, accessible through any one of the nodes, although each group has a 10 terabyte quota plus a 5 gigabyte user space. And then this is all connected to MIT through a 10 gigabyte link, so everything should be super fast. There are possibilities for expansion, although this is subject to space constraints. We'll talk a little bit more about that after the tutorial. The architecture of OpenMind is fairly simple, especially for those of us who are just starting out. There's a login node at openmind.mit.edu. This is not only the portal which you will use to connect, this is the address of the head node. You can use this head node for interactive use, for code development, and then we have the compute nodes, which are used to run either batch or interactive jobs on both single and multiple processors. They have names like node 001.mit.edu all the way up to node 32 or beyond at this point. Those nodes, the node names aren't necessarily important, but they can come in handy if you're trying to manage where in particular your jobs are going. To get an account, I think a lot of people have done this recently in this room, so I don't need to probably go over this, but anybody who is in a lab that has not yet requested, who's in a lab who is subscribed to OpenMind currently, but has not requested an account yet, you just need to send an email with the title of account request and then this message inbox, and usually you'll get your account within a couple of hours. As part of this account, you'll also get subscribed to the OpenMind mailing list, although there is a little hitch that you need to go in and set your appropriate notifications at your MIT GitHub to give it your primary email address. So how does OpenMind work? So I mentioned that it's run by an application, a tool called Srun, which is an open source application. It stands for Simple Linux Utility for Resource Management. You can get lots and lots of information at slurm.schedulend.com. It's designed for Linux clusters. It's used in many of the world's fastest computers. And it basically provides three key functions. It allocates exclusive or non-exclusive access to resources for some duration to complete tasks. It provides a framework for managing these tasks, starting, stopping, executing, monitoring on the nodes that they're running on, and it arbitrates between the different tasks that people want to run. So, for instance, it can do things like cycle running jobs through the nodes in circumstances where people want to run more jobs than we have resources for, or it can say, this person in particular has been submitting tons and tons of work, so we'll let this other person who hasn't been submitting very much recently to jump ahead of them in the queue and get their jobs done faster, that sort of thing. To connect to OpenMind, you need a little bit of software. I'm guessing a lot of people in this room, I see a lot of MacBooks, that's pre-provided. All you need to do is open the terminal application, if all you want is a command line interface. For Windows users, there are both GUI applications and command line applications, or those that support both. The one that I'll talk a little bit about here is called MOBA Xterm. I learned about this at the Boston University tutorials for their computing clusters, so you can learn a little bit more about that if you want to by searching their IT website. But I'll give you enough information here to connect using it. And so for Windows or Linux, you need your SSH client to log in. And then for file transfer, you need some sort of application that does file transfer. Again, for Mac and Linux, you can use functions which are built in to the operating system, such as CP or SCP for copy and secure copy, or rsync. And there are different tools as well for file transfer. For PCs, I know at least MOBA Xterm has a built-in graphical file manager, so you can just drag and drop files if that's what you're using. There's another thing called exporting. So if you want to use an application that has a GUI remotely on OpenMind, you just make sure that X11 forwarding is turned on when you connect, and then I'll walk you through an example of how you actually use that. Here are just some images of what you'll be seeing if you're using the terminal, or for PCs using MOBA Xterm. Here's the terminal component, and then over here on the left side, you'll get your graphical user interface, such as your file browser. For the terminal, there's no GUI. So if you haven't already, I want you to connect to OpenMind using this command, SSH flag Y, then your username at openmind@mit.edu. For anybody who doesn't already have an account or a demo password, I have Satra generated some demo accounts that I can pass out to whoever needs it. Everybody's good? Okay. Here you go. Oh, sorry. There you go. Okay. So if you have your terminal open, just type that in. I will do so as well. And okay. So I did ask people to go through a terminal shell terminal walkthrough prior to coming here, because there's not enough time to go through all the functions of the shell to sort of get people up to speed. But I'll give some comments as we issue commands here to sort of explain what the different components are. So SSH here is a command that you're issuing. Username at openmind.mit.edu is an argument of that command. And -y is an option flag for that command, which enables the X11 forwarding. I guess we'll start with interactive jobs, because that's, I think, what most people would be most familiar with, interactive computing. In general, on OpenMind, you're only going to use interactive jobs for debugging. So it can be tough, to write a script. To write a script and then not be able to go through line by line and debug it, but for that purpose there is this option. So I will do that here. So I guess this is the command you could run if you just want a terminal. Here, ohm interactive is an argument to the -p or partition option. So not only can the commands have arguments, but the options can have arguments as well. And if you want to use the GUI, you have to do something called adding a module. So there's a module which does the X11 forwarding from OpenMind. Here, add is a subcommand of module. If you want to see all the subcommands of module, you can type module -- help. For instance, I'll show you module avail is another subcommand, and if you type that, you can see all the modules which are available to us here. So let me just add this. And then partition. Then waiting for the job to start. So just like So when you submit a job, it goes into a queue. It won't necessarily start right away. For an interactive job, if it doesn't start right away, that can be sort of frustrating. But that's kind of how the cluster works. So if it's a really busy time, you might not have much luck running an interactive job. So now we're going to add I typed that wrong. Yes. And then for some reason it is not giving me. It may be. It's probably because I'm presenting here. I haven't tried it in presentation mode, but that should work for you guys. Okay. So then we want to exit MATLAB, and we want to. Sorry.
Remove the backslash at the front of the module name.
Yeah, that's what I did when I typed it wrong. I put that extra backslash, that extra forward slash there. And then we're going to exit again our interactive job, which will put us back on the head node. In general, the interactive jobs are limited to an hour, but when you're done, it's always good to exit out so that you free up the resources. The standard way of doing work on OpenMind is to submit batch jobs. Batch jobs are jobs which do not require user intervention or interaction to complete. Typically, each job will be defined by 2 or more scripts. The submission or sbatch script, which asks for a resource allocation and launches the job. And the job script or function or program which defines the actual task. For instance, a MATLAB function or script or Python or FreeSurfer or whatever application it is you're using. And the way you you start these jobs is by calling the command sbatch, which is a slurm command, with the argument of the script of the submission script. This command will return a string informing the user of the job ID number. So here before we saw that when we started our interactive job, it told us we were waiting for job 104.14226 to start. So that was our job ID. This can be more important. This can be important when you're trying to see how a job is doing, or if you're running any dependencies between jobs. And yes, these are numbered sequentially, so that is how many jobs have been submitted to OpenMind so far. It's a very big number. So when you submit a job, what you need to do is request resources. Resources are what Slurm manages. These are CPUs, memory, RAM, and sometimes GPUs. You specify these using the options. So the form is a single letter flag, option value, or long form flag equals option value, for example. If you want to submit a job script with one task on one processor, you submit sbatch-n1. Or you could say sbatch-n tasks equals 1. Just a little note, the equals only works with the long form flags, and don't put any spaces here. The shell can be very sensitive to white space. Typically, that's how it separates strings. Here are all of the resource options. C, which is CPUs per task. If you're not doing any kind of inherently parallel job submission, then this is the option that you'll use more often. If you want to submit a lot of tasks within one job, you'll use a different option usually. --mem specifies the real memory required, so like 100 or 50,000. You can also do memory per CPU in case you're running, you're using multiple cores and you need each core to have a certain amount of memory. N, number of tasks. I have a fragment there. Big N, which is the nodes, tells Slurm how many nodes you want. This can be either specifying like you need at least a certain amount of nodes, or you need no more than need no more than a certain amount of nodes. For instance, if you want all your jobs to run on a certain node, you can say -n1. And then T is the maximum amount of time that Slurm will allow your script to run. There's a hard limit on OpenMind of 1 week. If you need more than that, if you've got an exceptionally long job, you want to look into something called checkpointing, so you can save your work in the middle of a job and then start up a new one. And then a really good reference is
Just one note.
Yeah.
The default time limit is a day.
Good point. And then this website is a PDF document with a lot of good, quick information about the different Slurm commands and options that it's helpful. So here's a quick example. You guys can type this out. I encourage you to type this out. It's very short, it won't be hard. So what you're going to do is at the shell, you're going to type vim space testscript.sh or whatever. And then in the script, so vim is a command which opens up a word processor. And I'm just now realizing that I didn't include any information about how to actually use that word processor. I guess it's kind of annoying maybe if you haven't used it. But if you're going to do this, when you open up vim, just hit I. That allows you to essentially type. Then you can type this out. The first line here, it specifies to sbatch that this is a shell script, and it tells the interpreter, or it tells sbatch that the interpreter is the sh interpreter or shell interpreter. Sort of like the least common denominator interpreters. There's fancier ones, and actually the default. This actually points to a fancier interpreter on Macs and on OpenMind, but for simplicity, I'm just doing sh here. Now these three commands here are special syntax, which are actually comments, but sbatch will recognize these special comments as parameters. So instead of writing out these as parameters when you call the sbatch command to submit this script, you just put the parameters inside the script. So before the script even gets run, this gets scanned and the parameters get pulled out. And then what the actual task here is just to print the host name of the node that the job actually gets run on. So this is kind of fun. You submit this, and you get a file called slurm-yourjobid.out, in which the contents of that file simply list the name of the node that Slurm delegated this task to. Did anybody try running this and have any luck? Oh, good. Another Vim detail that I completely left out. So you're going to want to hit colon. When you're finished typing, just type colon, W.
Escape first.
Escape to get out of insert. Thank you. Escape to exit the insert mode, then colon, then WQ, and then enter. So that saves and quits. So I apologize for that oversight. Here.
In the submit, we would use srun scripting.
Submit, you're going to do sbatch and then the script name. Assuming you named it the same as me, it would just be sbatch space testscript.sh. Anybody have success? Good. Okay. No, so we have not set this up to tell us when it is done running. You can, though, and that is a totally awesome feature. I think in a later script I have instructions for that, but essentially you can have Slurm will email you when anything happens, when your job starts, when it finishes, if it fails. It's super awesome. So you're not going back and checking. And then this should be the contents of your output file. Super, kind of boring, but it's kind of cool.
So how do you load the output file?
Oh, so again, the output file, you're going to just type vim space slurm dash whatever the number that this command gave you dot out. And if you're not, if you lost it or you can't find it, just type the command ls. ls enter, and that'll give you a list of files in the directory you're working in. And you'll probably see a file that fits this format, and you can just run vim space that file. ls is the command that lists the contents of the current directory. Okay, so I'll move on. So srun is a command that somebody mentioned, and I didn't use in this script, but I could have. I personally, I'm a very basic user of OpenMind. I don't usually use anything that has explicit parallelism coded into the scripts. I'm either just using Slurm to run a bunch of similar tasks, or I'm running some MATLAB script that is using a par4 loop. But if you're doing some more advanced stuff, or using Slurm to submit a job which has multiple tasks, you want to use the srun command in front of the job steps that you're submitting in your script. And what this does, I won't read that, but it sort of handles that parallel job execution. It's not necessary for scripts which have only one task. Or run only one task at once, such as run this MATLAB script. And if you use it to run a non-parallel or non-MPI task in a script where either n or little n or big N are larger than 1, the script will be launched n or n times. But these numbers sort of have to have compatibility. Slurm will adjust the big N to fit what little n is.
Just a question. So
Mm-hmm.
in your example, if we had done this, then would it have run those two post-game commands in parallel?
No. You see, so for instance, this next one here. So this is sort of showing what happens when you use srun. So here we've changed the resource parameters. Now we want 2 nodes, 2 tasks, and we put srun in front of these. So what will happen here is that we'll run for each srun command here, 2 tasks will be launched. And these 2 tasks will be launched on 2 different nodes each time. And so when we run this is the output that we get. Node 2, node 3, node 2, node 3. So that's what the srun command buys us here. And there are other, this isn't the only function that does, the only command that does parallel job control either. There's way more advanced stuff that we're not going to get into here. Is anybody going through this and entering it? I'll sort of wait and let people do that. And I don't know if anybody noticed, but I actually left a typo here. This is actually what is the prescribed way to announce your shell script to batch in most resources by saying hashbang bin bash rather than hashbang bin sh. But for our purposes here, it's exactly the same thing because sh points to bash. Bash is just an extended version of the very basic shell scripting language implementation. Anybody get this submitted? Good. So can I? I'll move on then. So there's many options for SBatch. Most of them probably most of the people in this room will never use, but there are some that are fairly useful. You can submit an array of jobs, which is similar to using the -n option, but it just handles the submission a little differently. This is an easy way to, for instance, submit a bunch of jobs, each with a different parameter, which is indexed by this slurm array task ID. There's a dependency option. So, for instance, if I submit like 5 jobs and I need them to happen in series, I can have each successive job pass to each successive job the job number of the previously submitted job, and that job will wait until that job finishes or fails, whichever, to run. One kind of quirk about this, though, is that you can't get Slurm won't give you the output, the job ID as an output. It'll only give you the string, so you have to parse that string to get the job ID, which is not really hard, but it's annoying. Mail type, which is the option you want to use if you want to email yourself, or you want to have Slurm email you with updates about your job, and then mail user, which is your email address. You have to use your full MIT email address. If you just write your MIT name, it'll just send a local email to your user account. Partition, this requests a specific partition. For instance, there is a specific partition for interactive jobs. You have to request that partition if you want to do an interactive job. But it's also, I find it's, oh, no, never mind, that's for nodes. Then QoS, request of quality of service for the job. This really only comes into play if you need a job, if the cluster is really busy and you need a job done like today, right now, you have a deadline coming up. All of the groups have their own QoS, and if you request your group specific QoS, you will preempt or boot essentially other users who are working on the general QoS who don't have super highly urgent work. But don't do this unless you really have to. Then there's node lists. For instance, you can request specific nodes or exclude nodes. I always exclude the nodes that are included in the interactive partition, because what happens if you get I don't know if it's still like this, Sasha, maybe you can correct me. Is it not like that anymore? Oh, okay, never mind. It used to be the case that if you accidentally if you happen to get put on the node that the interactive partition runs on, and then somebody runs an interactive job, you'll get booted. But I guess that's not the case, so maybe that's not so important anymore.
And the one thing to point out is the way the queue manager is set up, that requesting a specific list of nodes no longer works. What the queue manager does is it takes the job and just distributes it to the node with the least load on it. And as a result of that option, you cannot request a specific node anymore.
I guess that's a good point, just to bring up the fact that, whether or not certain options work depends on the configuration, the configuration of our particular cluster. So if you go to the man page for SBatch, a lot of the options that they have there you can't even use.
Does it yell at you if you ask for
Yes.
option?
So if it doesn't work, it will yell at you. That's the good news with most things.
Okay, so, well, this may or may not be useful to you. It's useful to me because I do electrophysiology, but so I showed some toy examples, but I think to really sort of illustrate the power of what the computing cluster can be useful for, I've written out a full workflow a toy workflow, but it can be adapted really easily to your own data to do some offline spike sorting using a freely available Python package, which was written by some people at University College of London. This is actually a software package that is pretty old, but has recently been updated. And this is done by the original. I think the original program was done by Kenneth Harris personally, and now he's got a lab and a team of people who are writing some pretty cool software. So we're going to go through and install the software, because this is not so straightforward if you don't know the ins and outs of how to install Python applications. We'll write a batch script to sort multiple experiments simultaneously using the OpenMind cluster, and then we'll view and manually edit the results, although I don't know if the viewing is going to work for me right now. So why this example? So a lot of people in academia are creating these powerful open source data analysis tools, like Satra has created NiPipe or worked on creating NiPipe. And many of these are great use cases for the OpenMind cluster, but they're not always straightforward to install, and they're not always pre-configured to be run on a computing cluster. So just a little bit of background about Conda and Python environments. An environment consists of the settings and software, including the particular version of Python that exists around the programs that the user runs. In some cases, it's useful to have multiple environments when using multiple tools, which are dependent on different versions of supporting packages, or Python versions even. So for instance, the newest Python version is, I think, 3.5, but a lot of people sort of really rigidly prefer 2.7. And so some applications only work with 2.7. And so if you have tools that use both, you can't. It can be tricky to manage that. So something like Conda, which is a package manager and environment manager, does things like install, run, and updates packages and handles their dependencies. And it does this through segregated environments that live on your computer, and you can sort of switch between them as you need. Mini Conda is a light distribution that includes only Conda and Conda build and installs Python. We'll use that. There's also another one called Anaconda, which also installs or comes with prepackaged a bunch of typically used scientific packages. But we're going to use Mini Conda to sort of keep it light here. So because of time, I'm not going to actually ask people to do this right now. Some of the steps take a few minutes. After I finish and Satra does his bit, I'm going to come back to this. And for anybody who wants to stick around, I'll go through this step by step and make sure that everybody can make it work. Because it's kind of gratifying to get something like this to work with so many different commands, at least for a beginner. But what we're going to do is we're going to install, which is a 5-step, or however many step process, depending on how you segregate it. So you have to add the Miniconda module. We've already seen how to add a module. We're going to generate a file called condarc.condarc, which will contain the text nstrs : whatever directory you want your environments to be installed in. This is basically because as users of OpenMind, you don't have root access. And there's a lot of tools or applications that you may want to use that require root access. So in those cases, we have to come up with workarounds. And this is actually a relatively simple workaround. We just we just create an environment in our user space and install our software there. Satra, is the home directory actually 5 gigs now? Okay, so maybe I have this written to install all of this in the ohm partition, which has the 10 terabyte limit. I did that. I set that up for myself because at the time when I did this, there was a 1 gigabyte limit, and creating your own directory of Conda environments can eat up a lot of space really quick. So this configuration file, can configure various aspects of Conda. We're just going to use it to specify where these environments go. And like I said, this isn't the only situation for where lack of root access can require alternate software configurations. Then we're going to create the environment. And to do that, we're just going to start with by cloning the default environment, which is in the root directory. So we can install additional things to it, which is the reason we're doing this. We're going to use Python 3.4 because that's what we need to run the spike sorting program. We're going to install the dependencies. So Conda, like I said, is a package manager. So you have a subcommand of the Conda command installs packages. It sort of contacts the Conda servers, or who's the company? Continuum. It contacts the Continuum servers and sort of downloads these packages. And you're going to tell it to download them into the phi environment that you've created. You're going to get pip and numpy, matplotlib, all of these. This is just an option, so you don't have to confirm every install requests. Then you're going to activate your environment, and then we're going to use pip to do a few extra installs for programs which are not supported by Conda. So Python, Visby, which are dependencies for this particular program. And then we're going to install the actual program finally. And because this is a software package that consists of two programs, we're going to do this in two steps. Pip install clusterquick2, which is the clustering program, and then phi, which does things like spike detection and has a GUI for sorting through the spikes manually afterwards to fine-tune things. You're going to download the test data, and then we're going to copy over some scripts that I generated for you guys that you may have downloaded from the website already. We're going to update the PRM file. This is the only Python code that I have in the talk. This is just sort of saying because we're going to copy and make a bunch of different files, you're going to have to tell it to look for the script to look for the file in the directory that it needs to work on rather than hard coding it. We're going to copy the sample data and make 5 copies. Then we're going to, So one note here is that this interpreter designation is not necessary because we're running the script here using the sh command. The side note is that there's a bunch of different ways to get Linux to run shell scripts. This is just one of them. One note about what's happening here is that this is just some pattern matching to find the dat file that we want to copy. And then the rest of the function, the rest of the script just does the copying. And then I wrote this script to process the files in a bunch of different steps. And it's pretty well commented using the echo string display commands. But if anybody has any questions about how it works, I'll be here afterwards if people want to go through it. And then once you have that, you can submit process files. It'll traverse the directories and all that you've created for all the data files. And it will submit individual jobs to OpenMind. And it will email you when each of those jobs completes. And then afterwards, you can go through and do the manual part of this the spike sorting job. One thing that's useful here is if you want to check on submitted jobs, you use a Slurm command called sq with the parameter flag, the option flag -u, which is user, and then you write your username. Or you can write sq-j and the job ID. Just writing sq is going to give you something that's really ugly because there's always lots of jobs running and submitted at a given point in time. So this is a list of all the jobs that are currently running or submitted. I guess right now, how many? All of the jobs that are submitted are running. So the queue is empty right now. That's kind of interesting. And then if you want to sort of check on a job that has already completed, like you want to see if it failed and you want to see maybe what what happened, or if it's just stopped. Maybe it was preempted. You want to see what happened. You can use this command saccount, S-A-C-C-T, with the job ID. And then afterwards, we'll use you can use X tunneling to do manual sorting, or what I do actually personally is I install phi then again on my own personal computer, and then just copy over the sorted spike files to go through manually. So some more advanced topics that I didn't cover are, the biggest one is other parallel programming patterns. Everything that I showed, and I think what Srun will show briefly, are what's known as embarrassingly parallelism. That's where the jobs that you're submitting don't communicate with each other, essentially. They're all run as separate tasks. For more complicated tasks, there are other patterns, including those which don't require any kind of additional learning, really, or much additional learning, such as parallel loops, like in MATLAB, or GPU computing. Again, you can do that in MATLAB. Others require the use of special programming interfaces, such as message passing interface, or MPI, or OpenMP, or you can use them both together. GPU computing can also be a much more efficient implementation for certain problems. For instance, I'm sure you guys have heard of, the deep, all the deep learning that's happening. That a lot of that is done on GPUs. And then the other sort of advanced topic that I didn't cover, although Srun will touch on, is virtualization and containers. And so this is the containers and virtualization is sort of like an extension of what I talked about with the Python environments. You need to have a software environment to run your program, or maybe even more than that, you want to emulate an entire computer. And this provides a way to do that. It gives you sort of another level of portability, and it also allows for very or perfectly, I guess, repeatable computations across machines. Okay, so that sort of concludes what I wanted to show you guys, and I can hand it over to Srun now.